What's up, everybody? Welcome to the 11th lecture of trig. Today we're really just going to be going over a bunch of examples. To start off with, I thought we'd start with this example here. What we want to do is we want to get all of our like terms to one side. So to start off with, we're going to add sine x to both sides, and we're going to subtract the square root of 2 from both sides. And when we do that, what we're going to find is that we're going to have 2 times sine x is equal to the negative of square root of 2. Well, from here, we can divide 2 from both sides. So we're going to have sine x is equal to the negative square root of 2 over 2. So, looking at this, we can go back to our unit circle and we can say, all right, when is it going to be that sine x is equal to negative square root of 2 over 2? Well, there's 2 different spots, right? There's here, and this is when x is equal to this x, not our graph x, right? So this is going to be whenever x is equal to 5 pi over 2. My mistake. 5 pi over 4. Sorry about that. In the other case, it's going to be somewhere over here, and it's going to be whenever x is equal to 7 pi over 4. But we know that sine and cosine are both 2 pi periodic. So these aren't going to be the only 2 answers, are they? Now, once we make one rotation, we can make another one, and another one, and another one. Or we could go backwards, right? And every time we do that, every time we make one of those cycles, we're going to pass through these 2 points. So, because of that, we can't just say x is equal to 5 pi over 4 and leave it at that. No, we have to include every time we go through that point. And we're going to go through that point every 2 pi rotations, right? So, one answer is going to be n times 2 pi plus 5 pi over 4. The other solution is going to be 7 pi over 4 plus n times 2 pi. So what is n here? Well, n is the number of trips you make around your circle. We're going to start at 0. We're going to make 1 trip around. We're not even at 1 trip, right? We're still at 0 trips. We're at 5 pi over 4 radians. Then we keep going, and we get to 7 pi over 4 radians. Now we've made 1 full rotation all the way around. We do it again. Now we're at 5 pi over 4 plus 2 pi radians. Keep going. Now we're at 7 pi over 4 plus 2 pi radians. Keep going. 5 pi over 4 plus 2 pi plus 4 pi radians. 7 pi over 4 plus 4 pi radians. So forth, so on. Keep going on and on and on and on and on. So every time we make a rotation, we add an n, right? So we add a value. And that's why we get x is equal to 5 pi over 4 plus 2 pi plus n times 2 pi, or x is equal to 7 pi over 4 plus n 2 pi. It's only because we keep making these rotations over and over and over again. So we pass through that exact same point every rotation. And n represents the number of cycles we made around. So we have these 2 points. We make n many rotations. And that's what these are telling us. So let's look at another example then. So for this next problem, the first thing we want to do is move that 1 over to the other side. So when we do that, we're going to have 3 tan squared of x is equal to 1. The next thing is divide by 3. Okay. So we're going to have tan squared of x is equal to 1 over 3. Now we want to apply the square root to both sides. But when we do that, we're going to find that tangent of x can be equal to plus or minus the square root of 3. So, tangent of x is equal to plus or minus 1 over the square root of 3. Now why is this? Why do we get this plus or minus here? Well, we get it because if tan squared, or I mean, my mistake, if tangent is equal to 1 over the square root of 3, well, squaring tangent then, you're going to get 1 over 3. And if tangent is equal to 1 over the negative square root of 3, squaring it, we're still going to get 1 over 3. Notice it's because that negative sign cancels out when we square it. And the positive sign stays positive. All right. Well, I don't like having the square root of 3 in our denominator. So let's go ahead and try to play with this a little bit. One thing we can do is multiply the numerator and the denominator both by the square root of 3. When we do that, we're going to get the square root of 3 over 3, plus or minus. Well, there are only 2 regions that this could possibly occur. I'm getting ahead of myself. Let me not go this way. Let me, instead of talking about it on the unit circle, let's talk about it on the graph of tangent. On the graph of tangent, we can take y is equal to let me choose a different color. We can look at the line y is equal to the square root of 3 over 3, and y is equal to the negative square root of 3 over 3. Now when we do that, we find that that line intersects our tangent function in 2 spots. Before I go any further, notice that what I've done here is, instead of drawing tangent from negative pi over 2 to pi over 2, I chose to draw it from x equal to 0 to x equal to pi. And the reason why will be obvious in just a second. So getting back to these y lines, notice that we cross our tangent in exactly 2 spots. The first spot is when x is equal to pi over 6. And the second spot is going to be whenever x is equal to 5 pi over 6. But hey, tangent's periodic. So once I pass one of these points, after I go another interval of pi, I'm going to find that point repeats, aren't I? Because tangent is pi periodic. So just like that last problem, we have to tack on this extra term. It's not as simple as saying x is equal to pi over 6 or 5 pi over 6. No, we have to include all those other points. And the way we do that is, again, going to be by tacking on n times something. So in this first case, we have pi over 6. X is equal to pi over 6 plus n times something, right? Well, I just said that tangent's pi periodic. So every time we go a distance of pi from one of these points, we're going to end up with the exact same y value again. So if I were to extend this graph out, we would find somewhere over here, that's a horrible tangent, but we would find somewhere over here another point that is a distance of pi away from pi over 6. So over here, when we're writing our solutions, we can say pi over 6 plus n times pi. Similarly, same thing's going to happen to this 5 pi over 6. So we're going to have x is equal to 5 pi over 6 plus n pi. Again, it's because it's periodic, it's repeating. And we want to capture every one of those repetitions. So what we're really saying is, yeah, x is equal to pi over 6, but it's also equal to pi over 6 plus pi. It's also equal to pi over 6 minus pi. It's also equal to pi over 6 plus 103 pi. It's also equal to pi over 6 minus 37 pi, so forth, so on. Same thing here with this 5 pi over 6. So let's look at another problem now. So for this next example, the first thing we want to do is subtract 2 cotangent from both sides. Okay, subtracting 2 cotangent from both sides, we're going to end up with cotangent of x times cosine squared of x minus 2 times cotangent of x is equal to 0. Well, if that's the case, we can factor out a cotangent, right? Yeah, so let's do that. Factoring out a cotangent, we're going to find that this gives us cotangent of x times cosine squared of x minus 2 is equal to 0. Now this tells us something. What it tells us is that either cotangent is equal to 0 or cosine squared minus 2 is equal to 0. How do we know that? But we know that because the only way you can get 0 by multiplying two numbers is if one of them, or both of them, are 0. All right, so we now have two problems to solve then. We either need to solve, well, not either, we need to solve both with cotangent of x is equal to 0, or cosine squared of x minus 2 is equal to 0. Let's start with this cosine squared. I think it'll be easier. Starting with this cosine squared, well, we've got cosine squared of x minus 2 is equal to 0. Well, we can add 2 to both sides. Seems easy enough. Cosine squared of x is equal to 2. Now we can take the square root of both sides. Cosine of x is equal to plus or minus the square root of 2. But wait, cosine x can never be plus or minus the square root of 2. Why is that? What's happening here? Why do I know that this can never happen? Well, it's because of what the square root of 2 is, right? It's 1 point something, which is outside the range of cosine. It doesn't matter if it's positive 1 point something or negative 1 point something. It's still larger in magnitude. So it's outside of that. So this can't happen. And the reason why, again, is because the absolute value of cosine of x is always less than the absolute value of the square root of 2, plus or minus. So because of this, this can never happen. So we can ignore this case. That means we only need to worry about cotangent. Well, when is cotangent going to be equal to 0? It's only going to be equal to 0 when x is equal to pi over 2, right? Yeah, absolutely. So, cotangent of x equal to 0. This implies x is equal to pi over 2. But wait a minute. What I've got here is the graph of cotangent of x times cosine squared of x minus 2 is equal to y. Notice it equals 0 at a bunch of different places. It goes through the x-axis at a bunch of different places, over and over and over again. Not just that, it's pi periodic. So the distance between these two zeros is pi. So, yeah, cotangent's equal to 0 at pi over 2, but our answer is going to be pi over 2 plus n pi. Now we could have also seen that by drawing the graph of cotangent and looking at that and saying that, yeah, we repeat this 0 every pi interval. So again, cotangent of x is equal to 0 whenever x is equal to pi over 2 plus n pi. And what that means, what all of this means together is this part can never be 0. Never, ever, 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 ever. But this part can. And that part is only equal to 0 when x is equal to pi over 2 plus n pi. So the solution for when x, for what x values makes this to be true, the solution to that question is x is equal to pi over 2 plus n pi. Now I want to clarify something in case it wasn't already clear. I kind of just jumped into this so I understand how confusion might have occurred by now. What we're doing here is solving for the x values that make these initial conditions true. So what I mean is we're finding all the x values where this statement is true, where cotangent times cosine squared is in fact equal to 2 cotangent. We're looking for the x values that make that true. And we're doing it by massaging the algebra and factoring things out when we need to, and kind of working it down till we can get to something like this and say, all right, this is only true if x is equal to this thing. That's what we're doing here. Having said all that, let's carry on. So before we start this problem, I want us to first sit down and have a conversation for a second. Well, okay, I want to talk to you for a second. Because some of y'all are not watching the lecture videos as you should be, I'm going to implement what I call the question of the week. The question of the week is going to be a question that I ask randomly throughout the week in one of the lecture videos at a random moment and an unmarked time within the lecture video. And what I want you to do is to go to the discussion board on Blackboard and answer it there for that week. So for example, this week is QOTW-1, question of the week 1. And the question of the week this week has 2 parts. Part number 1, why aren't you watching the lecture videos? What is it I can do to encourage you to watch the lecture videos other than this question of the week? Because personally, I hate doing this. The second part is, and this is just so that you don't copy other people's answers. I want you to take the day you were born and multiply it by the month you were born. So for example, February 26th, for me, it would be 2 times 26 or 52. That's what I would write in. It's 52, and I'm not watching your lecture videos because you're boring as hell, or whatever it might be. Again, this can be found on the discussion board. It's in Blackboard, it says discussion, it's in that little tab with everything else. Having said that, let's get to this problem. All right, so this problem looks daunting as hell. It looks scary and not like something we want to do, right? Well, it's not that bad. The first thing we want to know is, because of this little part here in the interval, we're not going to have to tack on that plus n whatever part. We're just going to have to find all the answers between 0 and 2 pi, and that's it. Well, that's convenient. The next part is, if you look at what we got, 2 times sine squared minus sine minus 1 is equal to 0. Well, if you get creative with this, you might notice it looks kind of like a quadratic equation, doesn't it? Yeah. If we were to do something like substituting u for sine x, we're going to use that substitution. Our equation would look something like 2 times u squared minus u minus 1 is equal to 0. Well, we know how to solve these equations from algebra, right? To solve this, we're going to want to break this out into 2 parts. We don't want to factor this out. And our factors here are going to be 2u minus 1 and 2u plus 1, right? I mean, and u plus 1. I take that back. No. Our factors here are going to be 2u plus 1 times u minus 1. If we use our traditional factoring methods, right? Okay. Well, now, what we're saying here is that 2u plus 1 is 0, or u minus 1 is 0. Well, u is really just sine x. We're just using u to make this look nicer for us. So really what this is telling us is we've got a couple things going on here. First, it's telling us that this factors into 2 times sine x plus 1 times sine x minus 1, and all of that's equal to 0. It's also telling us that 2 sine x plus 1 is equal to 0, and or sine x minus 1 is equal to 0. Well, we know how to solve these. We're just going to subtract 1 from both sides, divide by 2 in this top case. And in this bottom case, we're just going to add 1 to both sides and solve it that way. So this bottom case is a lot easier. Let's start there. Sine x is equal to 1. Again, I just added 1 to both sides. Well, if sine x is just equal to 1, and we have to pick an x between 0 and 2 pi, well, where can our zeros be? What answers could we possibly come up with? Pi over 2. Any others? No, not really. Just pi over 2. So this tells us x is equal to pi over 2. And one way we could see this is if we were to graph this. This is from x is equal to 0 set x is equal to 2 pi. And right here is where sine is equal to 1. And this is the case where x is equal to pi over 2. So, the solution to this first problem, this first part, is just going to be x equal to pi over 2. Now let's solve this top part here. And just in case you can't see it because it's all smeared up there, I'm going to rewrite it. It is 2 times the sine of x plus 1 is equal to 0. And we're going to subtract 1 from both sides. And that's going to give us 2 sine of x is equal to negative 1. And then we're going to divide 2 from both sides. And that's going to give us sine of x is equal to negative 1/2. Well, this happens in exactly 2 places. 2. Drawing our graph again. Putting a line through y is equal to negative 1/2. We see that it happens in exactly 2 spots. Here and here. So what are these spots? When does this occur? Well, it's going to occur whenever x is equal to 7 pi over 6. And this is going to occur whenever x is equal to 11 pi over 6. Now, just like I said, let me make this more clear for y'all. Because we're working inside of this interval, we don't need to consider the values outside of it. Only inside of that interval do we need to consider. So the answer to this part, this top part up here, which is equal to 2 sine of x plus 1 is equal to 0, the answer to that is whenever x is equal to 7 pi over 6, or x is equal to 11 pi over 6. And that's it. Those are our 3 answers. We have 3 answers in this case, and those are them. When x is equal to 7 pi over 6, when x is equal to 11 pi over 6, and when x is equal to pi over 2. That's all I got for y'all in this problem. So let's move on. Let's look at the next one. So in this example, what we want to do is we want to solve for x when cosine of x plus 1 is equal to sine of x. And we want to restrict x to be in the interval from 0 to 2 pi. So let's be honest. This problem's a bit of a pain in the ass, right? Yeah, it is. But it's not impossible. And the way we want to start it off is by squaring both sides of our equation. So we've got cosine x plus 1, square it. Sine x, square it. When we do that, what we find, just realized I was walking out of the screen. When we do that, what we find is that this side becomes cosine squared plus 2 cosine plus 1 is equal to sine x squared. So sine squared of x. Okay? Well, that sine squared we know is actually 1 minus cosine squared, right? Yeah, so why don't we rewrite it that way? Now that we've rewritten it that way, why don't we subtract, or rather, why don't we add cosine squared to both sides? When we do that, we'll get 2 cosine squared plus 2 cosine plus 1 is equal to 1. Now we're going to want to subtract 1 from both sides. We're going to have 2 cosine squared plus 2 cosine is equal to 0. Well, we can factor that out. We can pull out a 2 cosine. When we do that, we've got 2 cosine x, excuse me, times cosine x plus 1, that quantity, is all equal to 0. Well, if it's all equal to 0, then that means either 2 cosine x is equal to 0, or cosine x plus 1 is equal to 0. We've solved a bunch of these problems now, so I'm not going to go through the process of how to solve these two parts. Instead, I'm just going to give you the solution to those two parts. The first part, 2 cosine x is equal to 0 whenever x is equal to pi over 2 or 3 pi over 2. And that's because we restricted it to the interval 0 to 2 pi. So we don't need that in pi, right? And the other part, cosine of x plus 1 is equal to 0 whenever x is equal to pi. Now, this is where things get a little sticky. Did you notice at the very beginning, what we did could have caused a problem. It could have caused more zeros to occur. So because of that, we have to go back and check everything. We have to make sure we didn't mess around with our zeros, like we didn't make up an extra 0. We have to check to make sure each of these terms are true. So, because I've already done it here and I don't want to go back and do it again, what we've got is cosine pi over 2 plus 1. Well, cosine pi over 2 is 0 plus 1. It's going to give us 1 is equal to sine of pi over 2. Well, that's 1. 1 is equal to 1. Okay. Cosine of 3 pi over 2 plus 1. 3 pi over 2 is 0. Cosine of 3 pi over 2 is 0. Plus 1, that's 1. Sine of 3 pi over 2, well, that's negative 1. So we've got 1 is equal to negative 1. So this doesn't work. Three pi over 2 is not an answer. From here, sorry, I was just checking my work and thought I made a mistake for a second. So from here, cosine of pi, well, this is negative 1, right? That's on the far left side of your circle. Negative 1 plus 1 is 0, and sine of pi is 0. So this checks out because this gives you 0 is equal to 0. So our answers then are going to be when x is equal to pi over 2 or x is equal to pi. And again, the reason why that is because by squaring both sides, we may have created an extra 0, so we have to go back through and check. When we go back through and check, we find that it did actually create an extra 0. And that's it. That's all there is to this problem. Let's check out the next one. So you might notice with this problem, it's slightly different from the others. And the way it's different is because inside of our tangent, we have a fraction now. It's no longer just x, now it's x over 2. Okay, so how are we going to handle this? Well, we pretty much do the same thing we've been doing the entire time. Subtract 3 from both sides, divide by 3, solve for that, and then we're going to do some more stuff. So what does all of this look like? Well, first move, subtract 3 from both sides. 3 times tangent of x over 2 is equal to negative 3. Divide 3 from both sides. It's going to be tangent of x over 2 is equal to negative 1. So let's stop here for a second. Let's pause. Let's think about this. What we're saying is that whatever x is, x over 2 is equal to negative 1, right? So why don't we, for just a second, use a substitution. Why don't we, for just a second, say, let's call u x over 2. Then tangent of u is equal to negative 1. Okay. Well, if tangent of u is equal to negative 1, this must mean that u is equal to 3 pi over 4 plus n pi, right? And it's n pi because, again, it's pi periodic this time. Cotangent and tangent are both pi periodic. Cosine and sine are both 2 pi periodic. So here we want to use n pi, okay? Plus n pi. Well, cool. What we've got is when we substitute in x over 2 back into u, what we've got is x over 2 is equal to 3 pi over 4 plus n pi. So now we need to solve for x. And to solve for x, we're going to multiply both sides by 2. X is equal to 3 pi over 2 plus 2 times n pi. Okay, why is it over 2? Well, it's over 2 because when we multiply this all, we're going to get the 2 cancels down here, right? 2 over 4 is equal to 1/2, and that's what we used there. Cool. So that means then x is equal to 3 pi over 2 plus 2 times n pi. And that's it with this. And I have one last problem for y'all. So really in this last example, I just wanted to make a note about what your solutions can and can't look like. But before that, let's walk through this. What we're trying to solve is for the x values that make this statement true, right? We want to find all of the x's such that secant squared of x minus 2 times tangent of x is equal to 4. Well, first, we want to notice by the Pythagorean identities that secant squared, well, that's equal to 1 plus tangent of x. Which means we can rewrite all of this now. When we do, and we subtract 4 from both sides, we're going to find that tan squared minus 2 tan x minus 3 is equal to 0. Okay? So factoring that all out, we're going to get tangent minus 3, the quantity, times tangent plus 1, the quantity, is equal to 0. So that means either this first quantity or the second quantity is 0. Okay. Well, if that's the case, then we know tangent x minus 3 is equal to 0, or tangent x plus 1 is equal to 0. This first one we know how to solve. Pretty straightforward. We've already done it 1,000 times over. The second one, though, I already tell you that it's going to be equal to the arctan of 3. Okay. Why? The reason why is because we want to add 3 to both sides. Tangent of x is equal to 3. And I have no clue what that x value needs to be. Nothing on the unit circle tells me. But I can apply the arctan to both sides. When I do that, I have arctan of the tangent, arctan of the tangent of x is equal to arctan of 3. Well, taking the arctan of tan just gives back whatever we're passing through tangent, right? In this case, it was just x. If it was x over 2, we would have gotten x over 2 back. If it was orangutans and gorillas, we would have gotten orangutans and gorillas back. I don't know. Whatever we pass through tangent, we apply arctangent to, we get that thing back. So, what we've got then is x is equal to arctan of 3. Now this is the point I wanted to make. Is this an okay solution? Yes. When it's not something that is obvious, or something that's like on the unit circle, so square root of 3 over 2 maybe, or 1 minus 1, or 1 over 2. It's not these types of solutions, the typical angled solutions. In those cases, it is okay to write the arc, whatever trig function of that value, but only in those cases. So, what I'm saying is, if it's not obvious or easy using your unit circle or known identities, what x is going to have to be, and just leave it in this form. This arctan, arcsine, arccosine, whatever. Having said that, I'll let y'all go. Have a good one, guys.